All right, guys. Could you please tell me? Actually, I'll tell you what. Start here. What's the natural log of 2? Go ahead and figure that out.
0.693.
0.693?
Yeah.
And, okay. And what's the natural log of 3? 1.098 stuff?
Yeah.
All right, now, let's just file that away. It's going to seemingly not have anything to do with the next thing we're going to do. Good. Can you guys make a table to investigate this in your calculator? Can you make a table? So, just to help you out, you would put in the y1, you would put 2 to the x minus 1 over x, right? And then you would just make a table getting closer to what? So for example, yeah. So maybe I could start at. Some of you guys don't quite understand what you need to do here. Some of you guys were supposed to get close to 3 and you did 1, 2, 3, 4, 5. Is that close to 3? Hell no. That is infinitely far away from 3. You got nowhere near 3. So what should I maybe do? Say again?
Oh, I said 0.1.
0.1?
0.01.
0.01? 0.001? That's probably pretty good. That's coming from the right. And then on the other side, I can do negative 0.1, negative 0.01, negative 0.001. Okay. Is that cool? And you could either have the table created by the calculator, or you can just plug this in and get each piece. Right? Has anyone gotten any distance with this?
It's about natural log.
What's that? Is this thing? Yeah, so if you do it, anybody do this one?
It's 0.711.
7-1,
71777.
blah, 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 okay. And then this guy?
0.6095. And then the one after that, 0.6093.
3, blah, blah, okay. And then the same kind of thing with this, right? Or it starts from, what's it do below here?
0.66697.
Is this one?
Yes.
6697?
Yes.
This is probably 69 something, right?
690.
690?
Yeah.
And then this is basically 693, right? Okay. You guys somehow, and this, right now this is disconnected from anything. We're just playing around with shit. We're just kind of reviewing chapter 2 kind of stuff, right? Ooh. But the neat thing we just realized is, do you see how there's a 2 here? And this came out to be the natural log of 2, basically, right? So what do you think I would investigate to kind of relate to this? 3 to the h. So if I did the same thing, oh, Jeff. Right. 0.1, 0.01, 0.001. Right. Right now, everybody should be very, very, very comfortable creating this table. If you're not, you need to come see me. You should be able to make this table pretty quickly. So I'll give you a minute to do that. Miguel? Are you out there? Miguel? And then what's, oh, you're Miguel. All right, guys, are you seeing the same connection?
Yeah.
I'm not gonna fill in, but basically you should get 1.098 as you come to. So obviously, if I put a 4 there, it's exponential. Okay. So then, what can we say? I'm gonna erase all this. What does it seem is true then? And again, this is, we haven't proven this. But if we did multiple ones, it would keep bolstering the evidence that this is true. So right now, what would you say this expression is equal to? Natural log of b. Now, what does this have to do with, Jeff? I don't know. So if we had a function, right? So we know polynomial derivatives now, right? If it's the question is a polynomial, that kicks a lot of ass. Polynomials are easy derivatives. Do you guys, even though we just learned it, do you guys kind of agree with me? The power comes down, it goes down by 1. Woo! Okay. This is a completely different function, yes? This does not look like that rule. I get people that try to tell me that this is bring it down, go down by 1. This is bullshit. There's no reason it should follow the same rule because it doesn't have the same form. It's a completely different function. So how do I investigate this guy's derivative? What do I have to use? What's the only way we know how to do derivatives, really, so far, besides the few shortcuts we know? The limit definition, right? Oh, yeah. All right, sorry. So here's the function, right? So what would this look like for the limit definition derivative? Yes?
B plus h here. Oh.
B to the x plus h.
B to the, right? Because it's f of x plus h, you put an x plus h here. Minus f of x, so b to the x, all over h. Right? Now here's you guys ready? Real quick, Simon. What is this?
Fifth.
All right, good. All right, x to the 5th, not x to the 6th. Let me ask you real quick. Let me ask you a really weird question. In this expression, is there a 2 in there somewhere? No, there's no 2 up there. There's no 2s anywhere in this expression, and this is where some of you guys are like, which meds is he supposed to take? Why didn't he take them? This symbol here means what? That there are 2 x's. There's no number 2 in here. Yes? So why would the answer be 6? I'm not multiplying 2 and 3. I'm multiplying 2 x's by 3 x's. So if I have a string of 2 x's and 3 x's, this is a string of freaking 5 x's. Of course, I'm sorry, this is very basic shit, but people still kind of don't fully grasp why the rule is what it is. But that's all it is. Let me be really specific. Right? So, think backwards. How could I rewrite this?
B to the x times b to the h.
Yes. Become an h. There we go. Yes? Yes? This is something we really don't think about, is going backwards with that, because we normally don't have to. But does anyone see what can happen now? By b's and h's, this is really a problem.
Now there's only a b to the h on top. Negative window, just b to the h on top.
What can I do on the top? Factor out of what?
Or
What's left?
b to the h minus
minus
1.
1.
All right, Jeff, do a better job. B, H, there we go. And I'm going to put the over H here. So it's the same thing, right? Same thing. So what's the limit as H goes to 0 of something that doesn't have an H in it? What does B to the X think about H going to 0? Does it give a shit? No. So that's B to the X. And what did we just say this limit is? What did we just say
Oh,
that limit is?
natural log of b.
Yes? Natural log of e, yes. So we have a new rule. We have a rule. If I'm given, I've got to be mindful of you, my camera, not you, anybody. If I'm given y equals b to the x, then y prime, look how weird this is. It's itself times the natural log of the base. That's the rule. So, for example, f of x equals pi to the x. Yeah.
Is there a name to this rule?
No.
No,
It's just the, we could call it the exponential formula rule. I don't know, the book probably calls it something. What would this derivative be?
Natural log of pi.
No.
Pi to the x times
Good.
an x.
So any exponential function, the derivative is basically itself.
Times the natural log.
Yes. So can somebody tell me which base is kind of like the most interesting base for a form of like this? Pi is not very interesting. I mean, yes.
E to the x?
E. I'm with you. Why? What happens if the base is, what happens if I have the function e to the x?
Because
Cancels out.
derivative becomes
Where am I going?
e to the x times L and e.
Yeah, f prime, for something in this form, constant to a number, constant to a variable, sorry. And what is e about?
2.7.
I like it, that's fine. So this derivative is itself times the natural log of the base, and the natural log of e is 1. So there's an example of a function that is its own derivative. What does that mean visually? If I have e to the x, and I have to go draw its graph, what's true about the slope back here? It's getting really close to what? 0, but it's a little bit positive or negative? It's a little bit positive, yes? So it's a little positive, and what's happening as I move? What's happening to the slope?
It's greater.
It's getting bigger and bigger and bigger positive. Holy shit. So, taking a step back. One place e came from is the realization that the limit as h goes to 0 of e to the h is the only thing that hasn't come out to be exactly 1. E is that special base. So that's one place that we see e naturally coming out, which is another reason why we gave it a letter. E. So what's special about the number 2.71282, blah, blah, blah. It does this. This is one thing it does. It does several things that freaked us out, right? Why did we give pi a symbol? Does anyone know? Why did that number get a symbol?
Because it's too long to quantify.
But who cares? So is 4.7394666 forever.
It's also the exact circumference of
No, almost. It's half the circumference of a circle of radius 1, right? No matter how small or big a circle you make, if I take the circumference divided by the diameter, I always get the same number. So ancient civilizations, like the Egyptians, had an approximation for pi because they noticed this. No matter how small or big the circle is, so you could even, if I wanted to, I could bring in string, I could put it around the base of a trash can or something, and then the length of the string would be the circumference, yes? And when I do it as a circle, I can measure the diameter. And when I divide, I get something close to pi. Close because we're silly humans. I can't measure things very well, but it would be close. All right, sorry. So we got one more rule. Okay, so let's build another rule. This is on that paper. Did anybody not get that differentiation paper from last time? I think, did you need one? Yeah. We worked on this one last time. Here's that thing on that paper about the sine derivative. So if I wanted to figure out f prime, I would do this. Does that look like, can you multiply by the conjugate? That wouldn't do shit for me. Can you factor? What the shit? What can we do with this? What is the trig identity for sine of a plus b? Yeah, remember sine is nice, cosine is an asshole. Sine says, hey cosine, let's take turns. I'll get the A, you get the B. There's a plus, so I'll keep it as a plus. And then I'll get the B and you get the A. Cosine would be cosine, cosine, I'm first. You got a plus, screw you, it's a minus now. It's a sine, sine. All right, and again, that's just a silly way to remember. All right. So, what is sine of x plus h? Okay, so now we can break this up. And again, this is not distribution or anything like that, correct? Sine doesn't distribute, that's bullshit. This is just a rule that hopefully your pre-calculus teachers showed you why that's true. I love the proof of why that's true, it's really funkadelic. But anyway, if they didn't do that, that is true. Sine x cosine h plus sine h cosine x. So that's this, bam, minus sine x over h. Now let's break this thing up. I don't know if you guys, well, real quick, this first piece should be simple. Let me look at the top here. How do I want to write this? That's great. What's the limit as h goes to 0 of cosine h? As the input goes to 0, what's cosine of 0? 1. It's continuous through there, so I can just put a 0 in it. It's fine. So this would just be sine times 1. So is that cool? Sine x? Yeah. And there's a minus sine x. That kicks x. Right? Done. And then this guy, you just throw him here. Jeff Coleman. This is the one, I don't know if you guys remember, we did talk about this piece here. I don't know, does anybody remember what this does? Goes to 1. The smaller the input, the closer sine gets to that input. And we did that before, we actually looked at some examples. This goes to 1. So what does this mean? The derivative of sine is cosine. Which, if you look at the graph, again, if you look at the visual, it makes sense. If I have sine, okay, and I start to graph its derivative, would it be 0 there? 0 there? Isn't it negative here, approaching 0, and then it's positive through there, positive through there, and that's the most positive. Oh, Jeff, you're really doing a great job. Positive through there, and then it's most positive here, and then it's 0 again, and then it's negative. So now that's been shifted over, and now that's cosine. Crazy shit. Now, if we did the entire thing, let me stop. I know I'm going a little quick, but there's nothing too intense in here. Okay. So again, that's another rule. That's another rule you need to memorize. Derivative of sine is cosine. Okay. We'll get to the other ones in a minute. Because we can't, so for example, if I tried to figure, what would I need to know to figure out the derivative of cosecant, for example? What is cosecant? 1 over sine. 1 over sine of x. Do I know how to take the derivative of the reciprocal of a function? No, I don't. So that's the next thing we have to do. I kind of want to figure out all the derivative rules for all the trig functions. Maybe some of you guys are with me, maybe some of you guys are not really, but we all should. You all need to, because you need to know. But we need now to figure out some other rules to help us solve those. So what we try to do when we start to build shortcuts for derivatives is we figure out through the limit process the derivative of sine, for example. Cosecant is related to sine. Maybe there's a shortcut because we know what sine is. Maybe there's a shortcut to figure out what cosecant is. Right? And we will know that cosine's derivative is negative sine. We'll see that in a bit. And then I could do tangent if I knew how to do the ratio of functions. We don't know that yet. I love you guys. Okay. So, what we're going to do. What we need to be able to do. So, for example, let me give us a concrete example of what we're about to do. If I had a function that was, 3 to the x times sine x. We know the derivative of 3 to the x, correct? And we know the derivative of sine x, correct? That function has those in it, but is that function either one of those? No, it's kind of both of them, right?
Isn't them multiplied by each other?
No. So real quick, I love this. Real quick, just to show you. You might think the derivative should be derivative times derivative. Maybe? Let me quickly show you that's not true. Derivatives never work like that. They're more complicated. I should never expect the derivative of several things to be just all those things separately taking the derivative. I shouldn't expect that because derivatives are a little more complicated. This is going to be a little strange. If y is x squared, what's the derivative? Holy shit. Okay, now, what's another way to write x squared? Isn't there another way to write x squared x times x? So if I thought the derivative of the product of two things was just the derivative multiplied, yes? What's the derivative of x? 1. What's the derivative of x? 1. Then I would get 1. Is that right? No, screw that. Nope, sorry. So if the product idea, that's like my 8th puberty. If the product idea doesn't work for something as simple as x, it ain't gonna work for freaking 3 to the x sine, right? So what we need to do, instead of getting bogged down and trying to prove every possible function that's a product of things, let's just prove what the product of anything does. Let's just do all of them all at once. And you're all like, show me, math boy. Okay. So what we're going to do, hold on to this. We'll do this later once we figure out how the hell to do it. Let me define. So here I've captured basically every single function that is the product of two functions. There it is. That's every. I just wrote an infinite number of things down. And it didn't run out of.
Is that a minus or a?
It was a times. It was an emphatic times. So if we do this, I could apply it here, of course, because what would f of x be? 3 to the x, and what would g of x be? Sine x. So whatever I do here will immediately apply to anything like this, any product of functions. Isn't that cool? Okay. So this is kind of the idea. We're going to look at specific functions so that we can then build from them. And then we want to look at these overarching ideas. What if I multiply two things that I know? I would hope there'd be a way to use what I know. Okay. So what I'm trying to figure out now is, what is this? And of course,
F prime of x plus g prime of x. That's what we did yesterday.
no. So again, what we did yesterday, how is it different than what we did yesterday?
Oh.
Right, we did something like the addition, right? And why would this be easier? Because what is the limit? Isn't it f of x plus h minus f of x over h? So should the plus minus, if it's a plus in there, should it play better with that idea? I don't know if you guys, so we did look at this and I did kind of prove it and separated stuff. So here, this is completely different. I should expect this to be harder, and you'll see immediately when we write down the limit definition. What would that, love you guys, what would the limit definition look like?
That's so gross.
Don't give up hope. And again, you're not gonna have to do this. There's an exceptionally weird ass thing we're gonna do, but the minute you see it done, it's gonna open the door to, well, when else can I do that? Any damn time it makes sense. This is such a beautiful. I feel so, real quick, I feel a lot of pressure because this is so fundamental and it's so neat. And I need you to understand this because then everything else in calculus is going to make more sense. There's a little thing that we do here that's actually very useful in places. So I really want you to see, you don't even know you're allowed to do it yet. You're going to in a minute. So help me out. What would this look like? Let me, go ahead.
F of x plus h minus f of
No, stop.
Huh?
All right, let's do this.
Huh.
Wouldn't this be m of x plus h minus m of x over h, right? That's what m prime is by definition, yes? Okay. What is m of x plus h? M of x plus h.
F of x times g of x.
No, come on. What is m of x plus h?
Oh, of
What do you do with this? Don't you plug it in?
G plus H.
F of x plus h. Please don't take this wrong. That's the most mindless thing in math. Function notation first step is the most mindless thing. Whatever the shit's here, throw it in there. That's all it is. Now, at the same time, I understand there's a lot of shit going on. You kind of forget whatever, but that piece, just put the shit in. And of course, this is this. There we go. How do you guys feel about that? Be honest. What does that look? Does anyone have an idea where to go from here? Can you factor anything? Shit, no. Right? Okay. So here's the trippy thing. Here's the thing that you might not realize you're allowed to do. Which way should I do this? Yeah, let me do this. Let me do this a little bit different way. What way did I want to do it? Okay. So somebody help me out. Little side note. It's going to seem so out of nowhere. I'll do this. All right. Everybody see what I wrote down? Yeah, somebody might be out there saying, I see you wrote something down. But you're a little excited, Jeff. You need to, can't write too well, period.
Is that a negative on the outside?
Yep. So what is this? What is this?
Zero.
Zero, right? Yes? That expression is another way to say zero. Yes? 0 like 7 minus 7 is another way to say zero. Yes? Can I then add 7 minus 7 to anything in the universe and not change it? Yes. I really want you to understand. You have 5. Now add 7 minus 7 to it. What is it? Freaking 5. So are you allowed to do that anywhere you want to? Of course. Would you? No. That would be weird as shit. But this expression, I can insert it into that, and it would be the same thing. Yes? Because this is 0.
I see. You're gonna.
Somebody's looking ahead. I like it. Now, what does that look like? Okay, so how am I going to insert it? So I'm going to not give myself enough room, of course. So you can stop right now, Jeff. So now I'm going to insert this thing. Am I in the right? What? No, Jeff. Come on, you do it. There you go. Minus f of x, g of x plus h, plus f of x, g of x plus h. And then I've got this at the end. minus f of x, g of x. I almost fit it, almost. So this is 0, right? This piece is 0. So did I just write the same thing? Yes. I didn't change anything. I love you guys. Do you see how that's kind of silly on a certain level? Like, can you add 0 to anything you want to? Yes. How many ways can you say 0? An infinite number of ways, right? So there's an infinite number of things you could add to anything. And sometimes it would be useful to do that. What can I do with the first two things here? Do you see how there's 4 terms? So maybe I can group. What comes out of these two?
Gx plus h.
So I'm going to do something a little weird. Do you see how this is f of x plus h minus f of x over h, and I can pull the g of x plus h out? Right? Does that look familiar at all?
Then why are you less
Derivative of x.
Holy shit! Okay, and then over here I get plus the limit as h goes to 0. And what can come out of these two? Here it is, Jeff. What comes out of these two? F of x. Then I've got g of x plus h minus g of x over h. Everything's over h. Blue, you're dying. Blue, sorry. How's green? Green's okay. So like you guys told me, the limit as h goes to 0, this is f prime, yes. The limit as h goes to 0 of g of x plus h is, what do you get when you let h go to 0 of g of x plus h? Just let h go to 0. What do you get left? G of x, yes, I'll let you. Not like, I don't know, man. Everything's weird. If I let h go to 0, this is freaking g of x, yes. Why is that not hard? Because x plus h is freaking a line. It's continuous everywhere. I can just plug 0 in. Plus f of x, right? Because as h goes to 0, this guy doesn't give a shit. It's just an old f of x. Well, what's this? What was this? That's f prime. So what is this? This is g prime. Holy what? So how does the product of two functions operate as far as derivatives? I love this idea. You're going to see this every now and again. See how each one gets its own term? Did f get a derivative by itself? Yes. And g is left alone. And then g gets a derivative and f is left alone. They take turns. And again, this is just a way to remember. This was the proof. We just proved what every product of functions does. But now you can start to think of ways to remember this. They each get their own term. So let's before we do this, I want to kind of give a concrete example of that we can check. And the same one I used earlier. So if f of x is x squared, doesn't that mean that f of x is x times x? And we already know from this one that f prime is 2x. So it better come out to be the same answer using this. Or else this is bullshit. We could throw it out. We could leave. And everybody gets an A. So what is f prime? Well, what's the idea? This guy gets a term. So let me just do this. Plus, this guy gets a term. What's the derivative of x? 1 times x is x. Derivative of x is 1 times x is x. And what's x plus x? Frick, 2x. And again, just to make sure you guys understand, why the shit would you ever do this? You would never do this, correct? So why did I do it? Because I know the answer to that. And if I write it like this, I can use this and it better be the same answer. It's a beautiful little way to kind of feel out an idea to make sure it actually works. It better give you the same answers you got before I guess you. Okay. So let's try to do that guy. By the way, the book proves this an entirely different way, so you can look through that if you want to. I just really dislike the way they do it. So, if I have, I'm going to desperately try to lay some groundwork for you guys. We're going to learn, for example, what do you think we call this rule? It works for any function that is the product of functions, so we're probably going to call it the product rule. Right? We're going to have a rule for the quotient of two functions. And we call that Fred. Then we call that the quotient rule. Right? Holy shit. And then the freakiest one we're going to work on is if I have a function inside of another function, the composition of functions. And of course we call that the chain rule, and you'll see why we call it the chain rule when we get there. We'll be working on the chain. That's right. I'm not going to start saying this guy. So what I want you guys to get really used to, unless it's really simple functions, even if it's really simple functions, you should write the rule. What do I mean by that? The first step I'm going to do, I'm not going to take any derivatives. I'm going to do the derivatives next. I'm not trying to do too much at once in my head. What's the rule say?
That it has to be f(y) times u. F times x.
Yeah, so derivative of the first one. And then leave this guy alone.
And then g prime.
No.
Sine of x prime.
No?
Plus
Plus, thank you.
sine of x prime.
Then the first guy gets left alone. He's already had his turn on the Ferris wheel, right? I want to go. Okay. That's the rule, yes? So this seems like a little thing. This seems, and some of you guys are like, but if you try to race to the answer and you try to not do this for yourself, you start putting stuff in the wrong place and forgetting to do other things. Now I can see clearly. Let's see who remembers. Sorry? The rate, I said, so what's the derivative of 3 to the x? Who remembers? And of course the sign is still here. Write that better. Let me do this. Plus 3 to the x is just sitting there. What's the derivative of sine? Cosine. Done. Right. So to write this better, the reason I was, if I didn't put that in there, is like, is the sine inside of the natural log, right? That's kind of gross. So I will write this as 3 to the x sine x natural log of 3. Then there's no question what's going on, right? Plus 3 to the x cosine x. Sure. Simple rule leads to really gross looking things. Okay. Okay. So let's do, let me think, do I want to, there's not a lot of interesting things we can do yet. Product rule by itself is a little lame, to be honest. It has to be paired with that chain rule thing I was talking about that's going to come later to really see it fully. Because every problem I could make up, well, let me make up one more problem. Sure, John. So find g prime for this function here. What do you got, Jeff? Put it down. Put his thing down. I will. Oh, okay. Yeah. Sure. Yeah, sure. What? Some of you guys are staring at me. I don't know if you're just doing it in your head. If you're not sure what to do, you can draw a duck. So it looks like you're doing something. Preferably, you should try something. Because right now is the time to make mistakes, because I ain't never going to see that shit unless you show it to me. So make big ass mistakes right now. Do it. Or get it right. Do it. What two functions are we working with? 2x plus 5 is one of them? Sine x and I like that. No reason to distribute the sums. No reason.
Yes, sir.
Start to catch up to you. Write the rule. This does two things. Make sure you get everything and do the derivatives in the right places, and it reinforces the rule itself to help you memorize it. Right? What's the derivative of this? 2. What's the derivative of sine? Cosine. How that? Okay, not bad, right? Not bad. Okay. So let's do quotient rule. So how am I going to do this? Well, I'm going to set up m of x to be f of x over g of x. So you guys hopefully realize this is going to be even worse than the product rule was, right? Let's see if anybody, take a minute, can you try to set up what this looks like? Limit definition.
It's like the same thing, just the top part divided by the bottom part.
Say again, sir?
But would it be like the same thing, like the bottom, like top part divided by the bottom part?
Nope. It's going to be a bit more complicated, like quotients normally are more complicated. But I mean, the limit definition. You don't have to know ahead of time what it's going to end up being. This is going to be a little bit funky. I will tell you it's going to have fractions inside of fractions, right? Because what is m of x plus h? That's what's got to go here, right? M of x plus h. So what is that?
Or you want us to? Oh.
Yeah, what is m of x plus h? What is?
Oh, you wait. Do you want m
Alright,
of x
let me
plus
write this
h,
down.
or do you want what do you want?
Here's the limit definition. In terms of m, but now we know what m is. So what's this?
F of x over g of x plus h.
F of x, say it.
F of x plus h over g of x plus h.
Yeah, that's all it is, right? Whatever the hell that is, just put x plus h in there instead. Minus
F of x over g of x.
f of x over g of x. All right. Aren't you even less excited about this one now? Yes. Man, all right. What do you normally do when there's multiple fractions inside of a problem? What's the first thing you try to do?
Put it all under one denominator.
Try to get them together. I like it. So how do you combine these two?
Multiply the right one
Yeah,
by
what's he
g
need?
of x plus
The
h.
greatest
Here's coming on, mama. What does this guy need? That he's got.
g of x.
G of x. I like it. So times g of x times g of x. And what does he need?
G of x plus h.
Plus h. Now they have the same denominator. And real quick, this might seem kind of silly, but why do I not have to do anything down here? I always get one student at least that's like, you did stuff up here, why does nothing happen down here? I didn't do anything up here, did I?
Still.
I multiplied this by 1, and I multiplied this by 1, I did nothing. So why would I have to do, so I'll multiply the bottom by 1, done, yay. All right, just in case anybody was thinking that way. Now this is so much better now. F x plus h, g of x, minus f of x, g of x plus h. Now let's see if you guys remember, I talked about this before. All this shit could just go down here because this is being divided by both of them. So might as well just put them both down there. I don't know if you guys remember that. Okay, so that is the slightest bit better because there's no more fractions inside of fractions, but it's still like, well, let's see if anybody was paying attention earlier. What do you think I'm going to do now?
You're gonna put them all over fractions, so that you can just subtract from the top down. Not an iPad before it's.
Oh, okay, because I'm not sure what you're saying.
Exactly. I'm not either.
But what did we do with the product rule that you didn't know you were allowed to do?
Add a zero.
Added, subtracted something, right? I think about it like, how many people have never seen the first Indiana Jones movie? Anybody? Okay, but the rest of you, remember when they had the golden idol and then he put the sand there? So I can take something away as long as I add the same amount. Now, what did he do wrong? He balanced his equation incorrectly. Boulder running, people with bad aim throwing spears. They were like the stormtrooper equivalents in that movie. But if you've never seen it, okay. That's back when they knew how to make a movie. So here, I'm going to do the exact same thing. In the middle of this stuff, I'm going to add and subtract the same thing. So let me write this down, leave some room in the middle. Is that right? Yes. All right. So in the middle of that, I'm going to add and subtract the same thing. What was that, Jeff? There it is. Yeah, that makes sense. Let's see if this makes, wait, do I have to? Oh yeah, that's right. Okay, so I'll do this piece at a time. This gets a little weird. So I'm gonna, let's see if this makes sense. If I want f prime to show up here, isn't it kind of missing f of x, right? F of x plus h should be a minus f of x. Do you guys see that? And if I want g prime to show up here, isn't it missing a g of x to go with that, right? Even though it's kind of like in the wrong order. So what I want to do is subtract and add that. So everything I wrote in red is 0. Everything I wrote in green is what this is. So I've just done nothing. Okay. You guys doing okay? I don't know. You know, I keep going. Okay. So this first piece is going to be pretty straightforward. What can I do here? I can come out of these. Take a g of x out. I'm going to do sort of the same thing. Now here's where I need you to go with me. F of x plus h minus f of x over h. So I take the g of x out here. Is that cool? So I just took the g of x out.
Yeah.
And what's over? It's going to be over. What have I done? Hold on. Bum, bum, bum. I've done something strange. I hate when I do that. Wait a minute. Oh, okay. Everything's fine. Let me be a little. Yeah. This is fine. I'm just gonna write it a little bit differently than I was about to, or else it gets a little bit confusing.
I think it already is a little bit confusing.
No, I'm with you, but it'll get a little more confusing, I should say. All right. Part of my brain was worried because these should not cancel, but this is underneath both. So the only way the g of x could cancel is if they cancel out of both. So that's what I was worried about, because I don't want that to happen.
Where did the a's come from? Oh, it's brought it up there?
Totally. And didn't I take it down, or didn't I like take this stuff down? So, algebraic manipulation is also a little weird in here. And we're not used to doing some things we're doing here. So why am I, so if this is being divided by h, it's still being divided by h here. So I really didn't change anything, I'm just being more specific. This piece is being divided by h. It's also being divided by this business. But this now I can see is, the limit of this is f prime, right? Then I have, now look here, what's wrong with trying to get g prime? What's wrong with things?
It's out of order.
Out of order. So let me take a negative out. Doesn't that make this term positive? Minus. Yeah, we'll just keep that going on. Crazy shit. Boom! Boom. Okay. Woo! So there are little technical details here that we're not used to doing every day, but they are something I could do anytime I needed to. And here I need to, because I want to recover f prime. I want to recover g prime eventually. Now what can I do with this?
Factor all
Let me see if you guys are cool. We can factor in f of x out? Is this all right? You guys will hurt me? I don't want to rewrite the whole thing. Okay. Now, let's replace what we know. The limit of this is f prime. This is g. Minus f of x. What's this? This is the derivative of
G prime.
the limit of this is g prime. Get in there. And what happens in here if I let h go to 0?
It's just
G of x and g of x, so g of x squared. Don't you love quotient rule? Isn't it the best? Okay, now let me see if I can get you on my side without using the song. I don't know if anybody, does anyone know the song? The quotient rule song? Okay, all right. Okay, I'm not the biggest fan. I love music, don't get me wrong. But when you use it in math to remember things, it takes you away from the idea. Most of the time. Okay. But if you know the song, you like it, use it.
I think I know it, but we're just without the song. You don't know for sine or anything. It's just like the derivative of the top times the bottom minus.
Yeah, so my big thing is, all right, so let me capture the rule again. So if I have the quotient of two things, I want you to see how, by the way, real quick, let me see. All right. What's the derivative of this? I would have to write this so I could do the derivative. I don't have to use quotient rule, do I?
X to the negative 1.
X to negative 1. So what's this guy's derivative?
Negative 1 to the negative x to the negative 2.
Good. Doesn't it become negative? Which function is on the bottom of this? Which function's on the bottom?
G of x.
G. So when I take its derivative, won't it have a negative sign? Because it's on the bottom, it's got a negative 1 power if I bring it up. Yes? Maybe?
Yeah.
So, here's my song. I will use a song. Why not? I'm going to use a song. So for a quotient rule, the most important thing is which one to do first. So here's my song. My song is top first. Top first. I'm sorry. You guys are all like, sure you think that's funny, Jeff? That's all that matters, is I think it's funny. Top first. That's it. The top gets the derivative first. The bottom comes second. That's what's most important. Because when you do the bottom derivative, it's the one that has to be negative. I want that to make all the sense in the world because it would be to a negative 1 power. The negative would come down. So in this, why does it make sense that that is negative? Because the bottom dude, when you take a derivative, it's going to have a negative. We know that. And then you got this squared piece, right? All right. Nobody else knows this song? All right. My problem with this song, I don't even know if I can say it right now. High D low, like low D high minus high D low, square the bottom, and away we go. That's the thing. It's like a little saying. All right, but to me, you don't need that. G prime's kind of the negative, isn't it? Okay. So let's try a problem. What time we got? Okay. Yummy. This is really, would you guys agree? Is there a way to simplify this? Is there? Factoring won't work because it's not a square. It's not the- right? You can't long divide because that's bigger than that. So is there a way to simplify this? No. You guys understand? There's no real good way to simplify this. Now, if you have a suggestion, tell me. Yes?
You can just take the derivative. of the
No, no, no.
top bar.
So before derivatives, is there a way to simplify that? No, there isn't. Not any useful. So how do I do the derivative? So first, okay, so you take derivative of the top times the bottom. Just like quotient rule, they each get a turn. Top gets a turn first. Minus, leave the top alone. The bottom gets its turn. All over what?
All over bottom square.
All over. Schwamp. The bottom square. Now, real quick. I love you guys, but can I cancel one of these out? Why not? Because, yes, there's more than just this being divided by this. They're both being divided by this, and that's not even x cubed plus 2x minus 3 anymore. It's the derivative of the damn thing. So please don't, right? First step of the quotient rule, you will almost never be able to kill them unless there was something you could have killed here. So now it's easy. I memorize the rule, because you have to memorize the rule. And then write the rule, then do the, now it's gonna be easy. What's the derivative of x squared minus 1? 2x. What's the derivative of
3x squared plus 2.
Right? Is this cool? This is all boring shit. Whoop-de-doo, whoop-de-doo. Because now I gotta get the like terms together on the top, right? Okay. Where am I at? Okay. Let's see, this will be 3x to the 4th. There's a minus sign here. So I'm gonna do this and then change the sign immediately, right? So x squared times 2, and that's 2x squared minus 3x squared is negative x squared, so plus x squared. Minus 2, so plus 2. So the biggest mistake, one of the big mistakes is to forget that there's a negative here. It's going to affect everything that would be a result of this. All over, blah, blah, square, okay. Can you do this? Yes. As long as you establish what that is, that's fine. And then get my like terms together. Negative x to the 4th plus 5x squared minus 6x plus 2 over, now at the end you better put this back in. And I really doubt that would factor out or anything. Okay. Isn't that neat? And by the way, the more rules we learn and the more functions we kind of throw together, the easier it is to forget what this represents. What does this represent?
The derivative.
The derivative of this function at any point. Which is crazy, yes.
Are you ever gonna make us like prove the rule, the quotient rule?
Move the quotient rule?
Prove it.
Oh, prove it.
Like the way you did in the past.
It could, only as a bonus problem if I felt like it. Yeah. Because I'm not gonna make you memorize the proof, but you need to watch the proof at least, to start understanding the things you could do, yes.
Could you like move g of x up and then do the
Yeah, but we're not there yet. Because, so I love what you're saying. And in what you're saying is exactly what I did. So, to come clean, when I learned this, I didn't like quotient rule. I'm never going to do quotient rule because we learned chain rule, which you guys haven't learned yet. And there is, so what he's saying is, couldn't I take that function and write it like this? Isn't this a product rule now? But do I have a function inside of another function? Yes. Do we know how to handle that composition yet? No. So as soon as we learn chain rule, I could show, now you could really see though, if I do the derivative of this piece, won't it have a minus? That's what I was saying about this. When I do the derivative of the bottom piece, it's going to have a minus because it's on the freaking bottom. It would be to a negative 1 power if I brought it up. But we don't know enough yet to do this. Meaning, this is what's really hard for some of you guys. If you've ever taken calculus before, you can't use an idea from a future section in an earlier section. No. Right? Some of you guys were trying to do derivatives back in chapter 2. No. Right? That was before we knew anything. Okay. How do you guys feel about this? I mean, I really want you to understand there's not a lot happening there. There's very little calculus. You have to memorize the quotient rule, and then this was an easy derivative, and then the rest of it's algebra, which unfortunately, a lot of times, this is where the mistakes happen. But I mean, to be honest, it's really easy for mistakes to happen here, right? There's a lot going on. Yes?
Well, you said that the negative like contributes to like the x squared minus 1 and then times 3x squared plus 2.
Here, because look, isn't this on the bottom? Where am I? There. So if I brought it up, wouldn't it be to a negative 1 power? And I take the derivative of something to the negative 1, the negative 1 would come down, so it would become negative. So that kind of explains why in the rule there's a minus sign here, because that's the part where you're taking the derivative of the thing that was on the bottom. So it would have a negative 1 power if you brought it up. So again, it's just another explanation about why that's a minus sign. Now, of course, the other explanation is you saw the proof. So it just came in, a minus sign had to be there. That's period. But there's a little more concrete reason why it's there. Oh, you guys are so excited. I could tell. I could feel it. You're all like, holy shit, this is weird as hell, and we're like not very far in the course. What's coming up? Okay. How much time we got? Oh, we got a little bit. So let me do the very next thing I want to do. I think I had a little outline for myself. Did I remember everything? Yes, yes, yes. Okay, let's do this. The last thing. Last thing. For today. Don't get too excited. So let's remember one thing and establish another. The derivative of sine, what is it again? Cosine. The derivative of cosine, if we do all the same work we did earlier, it actually comes out to be negative sine. And you can actually see that if you graph cosine, you can see, let's see if I can do it real quick. Here's cosine. You can do it, Jeff. Right? So isn't it 0 here? But then what does it become after that? Negative. And there's 0 in there. Isn't this the negative of sine? Isn't sine supposed to be flipped? So sure enough, the derivative of cosine is negative sine. So, what the shit is the derivative of tangent? Do you want to do limit definition? I was going to say, if you do, you'll do it somewhere else. We're smarter than that. Don't we know parts of tangent? Don't we know rules that will help us? What is tangent, fundamentally?
Sine over cosine.
Yeah, sine over cosine. Isn't that a quotient? Do you start to see what I was saying earlier? We're going to learn specific things for specific functions, and then we learn rules for those functions doing shit with each other, right? So we know sine and cosine, and they're dividing each other, and we know the rule for things that are dividing each other. I don't know, what's the rule? How does it work? What's first?
Derivative of the top.
Top first, I like it. Times the bottom. Minus.
Derivative of the bottom.
Good. They each get a turn, divided by
Cosine x squared.
cosine squared. Derivative of sine is cosine times cosine is, right? What's the derivative of cosine? Negative sine. So is this cool? So the derivative of cosine is negative sine, so doesn't that make this a plus? Is that cool? Let me see. I like this. Alright, so you got cosine squared x plus sine squared x. If you don't know what that is, I don't know what to do for you. What is cosine squared plus sine squared? 1. Yes? Pythagorean theorem, the most fundamental identity. And what is 1 over cosine? Secant. So what's the 1 over cosine squared? Secant squared. So the derivative of tangent is secant squared. I like somebody had a reaction like, oh. Like, which is not. Would you have been able to guess that before I? Shit, no. Even if you drew the picture, you could maybe. But even then, it's like, oh. All right. So that's just an example of you don't have to kind of know where it's going to go because these are funky functions and we're doing weird shit with them, right? So real quick, how much time? Oh, I get. Oh boy, Red just wants to stay. Do cotangent. Good. Figure out the derivative of cotangent. Now I gotta get a better marker. Jeez. What is it? No. It's cosine over sine. So with the, actually, what you said is correct, I believe. Cosine over sine, so the cosecant over, that's true. But it's not a good thing to do here, because we don't know the derivative of secant or cosecant. See if we can start to figure out a pattern here. Right? What's the derivative of cosine? Negative sine, so I get negative sine squared. The derivative of sine is cosine. What's negative sine squared minus cosine squared? Negative 1, because wouldn't you take the negative out and then sine squared plus cosine squared? So it's negative 1. And what's 1 over sine? Cosecant. Oh, squared there. Now watch, this is kind of cool. Because you're going to have to memorize all this shit. Not the derivation, but the answers, right? So your sine is cosine, your cosine is negative sine, derivative of tangent is secant squared. Now watch this. Derivative of tangent is secant squared. Derivative of cotangent, negative cosecant squared. All the cos shit is negative when you take its derivative. What's the derivative of cosine? What's the derivative of cotangent? Okay, right? That kind of helps to explain why we call the co stuff, right? Has anybody ever wondered why sine, like cosecant should be cosine, sine and cosine? Has anybody ever felt like that? Like, why is this co? Well, you don't know until you get to here, and you start to understand the properties and the relationships. Okay, one more. Secant. That's one we don't know yet. So what is secant? I'll do it with you this time, just save some time. What is secant? And that is a quotient, yes? It's a little bit weird of a quotient. We're going to see something weird happen. So how do I do the derivative of that quotient? I take the derivative of the top minus 1 times the derivative of the bottom over the bottom squared. What is the derivative of 1? 0. Yes? What's the slope of y equals 1? 0. That is so simple to miss. So that's going to be 0 times who cares? Good. Derivative of cosine is negative sine times negative sine. Now watch this. Sine x over cosine x times 1 over cosine x. Is everybody cool with that? I just split that up. Because what's sine over cosine? Tangent. And what's 1 over cosine?
Or secant.
Secant. So I'm going to write it like this because this is the way I have it memorized. The derivative of secant is secant tangent. That's weird. So what do you think the derivative of cosecant is? Let me write this real quick. Secant x, tangent x. That sounds like a song. Secant x, tangent x, okay. Cosecant x derivative would then be negative, good. Cosecant.
Tangent. Cotangent.
Cotangent. Isn't that cool? That's true. If we did all the same shit, we get this. So we're not going to do all the same shit because that's just true. And that makes it easier to memorize these things, which you must memorize. Did I say that? Yes. Am I going to say it again? Yes. And again, you know that these problems will eventually ask you to figure out a tangent line at like 5 pi over 6. And I'm going to want exact answers. So if you still don't know your trig of basic angles, you are behind. You need to know your trig. You need to know those identities. Remember that sheet? Everybody seen that sheet on Canvas? Above that black line is everything I assume you know. You have memorized. So it can come up any damn time I want them to. I really want you to understand. I'm not doing that to be mean. I'm doing that because that's what I need to do in this class. Right? Is everybody going to take 280? 1, 2, 3 maybe? I like the maybes. That's cool. Some of you guys are like, I really thought it was, and now after this, I'm like, I don't know. And I'm like, damn, no. 280 is Calc 2, yes. I'm sorry. I love that was what the question was. I'm sorry. I work here, and I think 280 automatically. Everybody knows what it is. Calc 2. So several of you. Teachers teach 180 and don't do any trig in it, so their students do pretty well. And then they hit 180, right? They don't do any trig in it. Then they hit 280. And one of the very first things you do is just like crazy trig. And they're like, I passed 180 with an A. You're an asshole making me. No, you're supposed to know this. So part of my job, even if you're not going to take 280, I don't care. Part of my job is to get you ready for 280, which means you have to know your trig. You just have to. Right. That's enough. That's enough for today. So let me know if you have any questions. You can hang out for a bit. If not, I will see you Friday.
So this one right here?
Yeah.
Does that mean that